Get ready. Design junkies to torque your nuts, harden your springs, and forge that mind into a bulletproof study guide. We are mechanical engineering made simple.
Today we're doing a deep dive into the absolute bedrock of engineering design.
We're talking about the relationship between force and deformation, material constants that govern everything, and the critical methods we use to predict when, and maybe more importantly, how something is going to break.
Exactly. We've pulled from some foundational source material to really get to the heart of it all.
We basically distilled the core concepts of stress, strain, and material failure. The mission here is to give you a comprehensive shortcut, a way to really grasp the non-negotiable relationships and tools for any kind of a structural analysis.
And we have to start with the fundamentals. I mean, if you want to understand how a bridge stays up or how an engine block survives, you first have to speak the internal language of mechanics.
Which is stress and strain.
Stress and strain.
So let's kick off with stress. It's not just the external force you put on something, right? It's how that load gets distributed on the inside.
That's the key. And the sources use a great analogy. Think about being underwater.
Okay.
The deeper you go, the more pressure you feel. That pressure is essentially a distributed force. It's a perfect, simple example of compressive stress.
So stress, which we call sigma, is basically force over a given area.
Precisely. And we generally break it down into two types. You have normal stress, that's the pulling or tensile, and the pushing or compressive force that acts perpendicular to a surface.
And the other one?
And then you have shear stress, which we call tau. That's the rubbing or sliding force. It acts parallel to the surface.
But the stress at any single point isn't just one number, is it? I mean, the magnitude changes depending on the angle you're looking at. How do you possibly capture all of that?
And that's where the reality of three dimensions kicks in. To really describe the complete state of stress at a single point, you can't just use one or two values. You need to know all 9 components of stress that are acting on 3 mutually perpendicular surfaces. This gives us the classic symmetric 3x3 stress matrix.
And that symmetry is super important.
It's everything. If those shear stresses weren't balanced, that little element of material would just spin out of control. The symmetry confirms rotational equilibrium. It has to be stable.
Okay, so if stress is the internal cause, then strain must be the effect, the deformation. How do engineers actually measure how much something stretches or warps?
That's the language of strain. Normal strain, which is epsilon, is just the rate of change of length. It's dimensionless, so you can think of it like a percentage of stretch.
And shear strain is about the distortion, the change in shape.
Exactly. Engineering shear strain, gamma, measures how much an element's right angles change. It's measured in radians, and it's the direct result of those internal shear stresses we mentioned.
So we've got stress, the force, and strain, the deformation. The magic that connects them is Hooke's law. But it doesn't always apply, does it?
No, it requires a few key things from the material. It has to be linear, homogeneous, and isotropic.
Okay, break those down.
Linear just means strain is directly proportional to stress, a straight line. Homogeneous means the material is the same everywhere. And isotropic means its properties, like stiffness, are the same in every direction.
And if all that holds true, we get our 3 critical material constants.
Yes, the big 3. First, the modulus of elasticity, E, or Young's modulus. That's stiffness.
Right.
Then Poisson's ratio, nu, which is how much it thins out when you stretch it. And finally, the shear modulus, G, its resistance to shear.
But here's the really cool part, the thing that saves designers a ton of work. These 3 aren't actually independent.
That's the real insight. For these kinds of materials, if you know E and nu, you automatically know G. They are mathematically linked by the equation G equals E divided by 2 times the quantity 1 plus nu.
So if you test for stiffness and thinning, you get twisting resistance for free?
You got it. It simplifies testing tremendously.
Okay, so let's move from these ideal uniform stress fields into the real world where geometry gets messy. Let's talk about stress concentrations.
Yes, the enemy. Stress concentrations are engineering hotspots. They're these tiny, localized areas where the stress gradient just skyrockets because something has disrupted the smooth flow of stress.
And what are the usual suspects for causing these disruptions?
2 main things. The most common is a discontinuity. Basically, any sudden change in geometry. Think holes, notches, fillets, steps in a shaft.
And the second?
The second is contact forces, which create these really high stresses right at the point of contact that then fade away quickly.
And we quantify this spike in stress with the static stress concentration factor, K sub T.
K sub t is just a simple ratio. The maximum stress, sigma max, divided by the nominal or average stress, sigma nom.
And the classic textbook example is a hole in a really, really wide plate.
An infinitely wide plate, yes. In that case, theory tells us the stress right at the edge of the hole is exactly 3 times the nominal stress. K sub t is 3.0.
A 300% spike. But in the real world, plates aren't infinite. The source material you gave us had a real-world example with a measured K sub t of only 2.35. Why is it lower?
Because with a finite plate, the stress doesn't have an infinite amount of material to redistribute into. It kind of gets squeezed around the hole, which raises the nominal stress a bit, but actually limits that extreme peak you see in the theoretical case.
This is where we get to that counterintuitive aha moment from the sources, the idea of using a flow analogy.
Right. If you picture stress paths like streamlines of water flowing, a sharp corner or a hole is like a big rock in the stream. The flow has to jam up to get around it.
And sometimes the solution is to actually remove more material.
It sounds crazy, but it works. The example of adding 2 smaller relief holes next to a main hole is perfect. What you're doing is making the overall opening look more like a smooth ellipse. You're giving the flow of stress a gentler curve to follow.
So you're smoothing out the traffic jam.
Exactly. You reduce that sharp gradient, the K sub t factor drops dramatically, and the part is suddenly much more robust. It's a fantastic design trick.
But K sub t is the static factor. It only tells part of the story. The real world involves different kinds of loading over time.
Absolutely. The type of loading changes everything. Short-time static loading is what we use to find basic properties like yield strength, but then you have to add time to the equation.
And what happens when a load just sits there for a really long time, especially when it's hot?
That brings in creep. Creep is where the material slowly deforms or flows under a sustained load, even if that load is way below its yield strength. Think of a jet engine turbine blade.
And then there's the big one, the #1 cause of failures.
Fatigue, which is caused by repeated cyclical loading. A tiny scratch becomes a stress concentration, a crack starts, and with every cycle it grows a little bit more until bang. Catastrophic failure at a stress the part could have easily handled just once.
Speaking of limits, Hooke's law is great in the elastic zone. But what about materials that don't even have a straight line stress-strain curve to begin with?
Good point. Things like concrete or cast iron. For those, the modulus of elasticity, E, isn't a constant. So what engineers do is they use a secant modulus. They just draw a straight line from the origin up to a specific operating stress on the curve and use the slope of that line. It's an approximation for a specific load range.
Let's actually define failure. It means different things for different materials.
Completely different for ductile metals like steel, which can stretch more than 5%. Failure is defined as yielding, the start of permanent deformation. For brittle materials like glass, failure is just rupture, fracture.
So for those ductile metals, we have 2 main theories to predict when they'll yield. The first one is von Mises.
The maximum distortion energy theory, yes. Von Mises. It's a bit complex, but it basically says yielding happens when the energy stored from distorting the material shape reaches a critical value. It's generally the most accurate theory we have.
So you calculate this thing called the equivalent von Mises stress, sigma sub Vm, and when it hits the material's yield strength, S sub Es, that's it.
That's the prediction. And it matches experimental data incredibly well.
But it's not the one most commonly used for, say, safety-critical design. That's usually Tresca, the maximum shear stress theory. Why the simpler one?
Well, the maximum shear stress theory, or Tresca, is simpler, as you said. It predicts failure when the maximum shear stress, which is just half the difference between the largest and smallest principal stresses, S1 minus S3, reaches the shear strength at yield. But the key reason it's used so much is that it's more conservative.
Okay, how much more conservative? Why would a designer choose a less accurate theory?
Because it guarantees a bigger margin of safety. In the worst-case scenario, which is pure shear, Tresca predicts yielding at a load that's about 15% lower than what von Mises predicts.
I see. So it's a built-in safety factor.
It's a huge advantage. Less computation, and you get a guaranteed safety buffer. So von Mises might be for high-performance, weight-optimized research, but Tresca is for building a safe bridge.
Got it. And for brittle materials, it's a whole different game, using things like the Coulomb-Moore theory, which needs both tensile and compressive strengths.
Right, because brittle materials are often much, much stronger in compression than in tension. You need both to define that failure envelope.
Okay, let's pivot to how engineers actually solve these problems in complex systems. There are some powerful analytical principles.
For sure. The first is a total lifesaver. the principle of superposition. For elastic systems, it means the total effect of many loads is just the simple sum of the effects of each load acting by itself.
That sounds almost too easy. What's the catch?
The catch is that the deformations have to be small. Superposition fails if a load changes the geometry of the system so much that it affects how other loads are applied.
Can you give an example?
Sure, think of a long, skinny beam. You put a load in the middle, it bends down. Now, if you push on the end with an axial load, that axial load is now acting on a bent shape, which creates extra bending moments it wouldn't have otherwise. The effects don't just add up anymore.
I see. So it only works when things stay more or less in their original shape.
Exactly.
And what about problems where you have too many supports? Statically indeterminate structures.
For those, we use the method of consistent deformations. We have more unknown forces than we have equilibrium equations. So we add in equations based on geometry, the fact that the deflections at the supports have to be compatible with each other. A fixed support can't move, for instance. That gives us the extra equations we need to solve for all the forces.
Okay, enough theory. Let's get practical. How do we actually measure strain on a real part?
The go-to tool is the electrical resistance strain gauge. The concept is brilliant in its simplicity. You have a tiny metallic grid, and as it gets stretched or compressed, its electrical resistance R changes in a very predictable way.
So you're just measuring a tiny change in resistance to find the strain.
That's all it is.
But if you're analyzing a complex part and you don't know which way the stresses are going to run, you can't just slap one gauge on there, can you?
You absolutely cannot. You need 3 measurements. Remember, the general state of plane stress has 3 unknowns: the stress in the x direction, the stress in the y direction, and the shear stress, tau phi. To solve for 3 unknowns, you need 3 measurements.
Which is why we have the strain gauge rosette.
Exactly. A rosette is just 3 gauges arranged in a specific pattern, usually a rectangle or a delta shape, that gives you 3 independent strain readings at that one single point. From those 3 readings, you can calculate everything you need to know about the stress state.
So if you just put one gauge on a twisting shaft, you could get a reading of 0 and think everything's fine.
You'd completely miss it, because the principal stresses are at 45 degrees to the axis. The rosette is non-negotiable for unknown stress fields.
And the readings aren't perfect right out of the box, are they? You mentioned corrections.
No, 2 corrections are critical. First, for transverse sensitivity, the gauge picks up a tiny bit of strain from the direction it's not supposed to be measuring. Second, and more importantly, temperature. Resistance changes with heat, so you have to compensate for that, either with special self-compensating gauges or by using a dummy gauge nearby that isn't under load.
And briefly, there are other more visual methods, right? Like photoelasticity.
Photoelasticity is a beautiful classic method. You make a model of your part out of a special transparent plastic, put it under polarized light, and load it up. The stress patterns appear as colorful interference fringes. It gives you a full field map of the stress distribution.
Okay, that brings us full circle. We started with the theoretical static stress concentration factor, K sub T. But we have to end with the thing that really matters for longevity: fatigue.
This is maybe the most crucial distinction for any practicing designer. We use K sub T for a one-time static load. But for repeated loading, for designing against fatigue, we have to use the fatigue stress concentration factor, K sub F.
So K sub T is the perfect, clean, mathematical stress peak. But K sub F is what the material actually feels over millions of cycles. What's the final takeaway on how these two numbers relate?
The essential thing to burn into your mind is this. K sub F is almost always less than K sub T.
Less. So the material is actually tougher than the pure math would suggest.
In a way, yes. This difference is a measure of the material's notch sensitivity. At a microscopic level, materials just aren't fully sensitive to every last peak of elastic stress. If you designed your part using the higher K sub T value for a fatigue calculation, you'd end up with an overly conservative, heavy, and expensive part.
So in the real world, you have to look past the elegant elastic solution and account for the messy reality of the material itself. You have to know it's going to be a little more forgiving under repeated loads than a static calculation would tell you.
It's the difference between a textbook problem and a real engineered component. It forces you, as the designer, to understand that failure depends on a marriage of geometry and material science, not just the peak stress from an equation.
A perfect place to leave it. Moving from pure theory into informed practice. Thanks for walking us through this.
My pleasure. Always good to get back to the fundamentals.